Hi, everyone. Thank you for joining us today for the Architecting Multi-Tenant Solutions on Azure. Before I introduce our speakers, I have a few quick things to go over. Please take a moment to read our Reactor Code of Conduct. We ask that you be kind and respectful to everyone, including our speakers. We want the reactors to be a place everyone feels welcome. Please ask your questions using the live YouTube chat. We have some moderators that will be helping answer questions in the chat, and then our speakers may take a few questions towards the end if there is time left. In the chat, we'll also be sharing some links that go along with today's event, including the link to our Reactor Meetup page, and if you're interested in checking out any other sessions we have coming up. Today's session will be added to our Reactor YouTube page in 24 to 48 hours. And finally, towards the end, I will share a link to our Reactor survey. If we have a few minutes, we would greatly appreciate your feedback. So I am now going to pass it over to John.
Thank you, Dion, and hello, everybody. My name's John Downs. I'm an engineer in the Azure Fast Track team at Microsoft, and I'm joined today by my colleagues Paolo Salvatore and Paul Burpo to talk about architecting multi-tenant solutions on Azure. Now, in this session, we're going to be talking through some of the guidance that we've been steadily publishing to the Azure Architecture Center over the last year or so. Almost everything that we talk about today is covered in that guidance. So you can access it at this URL. And we're also still adding to the guidance, and we'd love your feedback and suggestions. We'll talk about that a little bit later on. I also want to acknowledge that producing all of this content has been a huge initiative with many different contributors from many different teams at Microsoft. It's based on all of our experience working with companies like startups, independent software vendors or ISVs, and other companies who build multi-tenant solutions and applications on Azure. So although there are only 3 of us presenting today, as you can see, there are a lot of people who have contributed their time and their expertise to the content, and we hope that you get a lot of value out of it. Now, before I go on, I want to clarify a point. You might know the term multi-tenancy as it refers to Azure Active Directory. In Azure Active Directory, every customer is represented by a tenant. And in Azure Active Directory, tenants can set up federations to other tenants, and they can do various other cross-tenant operations. These are all great features, but that is not what we're talking about today. We're here to talk about how you can build your own multi-tenant software on the Azure platform. Now, of course, you'll use Azure AD as part of your own solution, but we're not here to talk specifically about Azure AD tenants. Instead, we're going to talk much more broadly about how multi-tenancy affects every aspect of your solution's architecture and design. And while I'm talking about disclaimers, I'll add another one, which is that multi-tenancy doesn't necessarily mean that every single component of your architecture is fully shared. It just means that your solution as a whole serves multiple tenants. We'll unpack this a little bit more later on, but I just wanted to mention that first up as well. Okay, so as I said, our presentation today is based on the guidance that we've been putting together for the Azure Architecture Center. And the guidance is in 3 main sections. So firstly, we have what we call the architectural considerations for multi-tenancy. These are the key things that you need to think about early in your planning and design stages when you're thinking about a multi-tenant solution. Next, we have a set of architectural approaches for multi-tenancy. These cover each of the main categories of Azure services, and they provide some of the key patterns and anti-patterns that we see customers follow when they're building multi-tenant solutions. And finally, we have service-specific guidance. So many Azure services have particular features that can be helpful when you build multi-tenant solutions. There are also lots of different ways that you can deploy and configure specific resources to meet your multi-tenancy requirements. And we're building out a set of this guidance for the most commonly used Azure services. We've got 8 pages so far, and we've got more coming soon. Now, these 3 sections of the documentation build on each other, and they're also targeted at slightly different audiences. So the architectural considerations guidance is likely to be useful for senior technical decision makers. So people like chief technology officers, solution architects, those who think through the big picture of how a multi-tenant solution needs to work and the requirements that their tenants might have. And also I would say product managers should also get a lot of value out of this kind of content. Then the architectural approaches section is really targeted for technical leaders, so solution architects and lead engineers, and other people who decide on how Azure services will be used and connected together as part of the overall solution design. And then the service-specific guidance is designed to be a technical resource that's available to engineers and their leaders to pinpoint specific features that they should consider and to highlight any kind of gotchas or things that they should be aware of. So in today's presentation, we're going to talk through a subset of all of this guidance, and we're going to help you both to understand how multi-tenant solutions can be designed, as well as the resources that we've got to get you to the next level of detail. Okay, so the first concept we need to clarify is what is a tenant. So a tenant is a broader concept than just a user. For example, one tenant might have multiple users. And if you're building a SaaS solution, then usually a tenant is a customer. So let's look at some examples. Imagine that you're building an accounting or a bookkeeping system that's sold to companies for handling things like payroll, expense management, banking, so forth. So the customer of your accounting system will be an organization. And they'll use your system to store their financial records, which of course will be associated with them. And that organization might have multiple users, each of whom use the accounting system. And they all work with the same data, although of course they might get different permissions to access or change that data. And those permissions are enforced by the accounting system. Now, multiple systems can each use the accounting system independently. They all have their own financial records and they all only see their own data. And they also have their own sets of users. Each one will have a commercial relationship with you as the vendor of the accounting system. So we call this a business-to-business or a B2B system. Now, typically in a B2B system, tenants are the organizations who use your system. Now, let's consider a different example. Think about a music streaming service. So you might subscribe to the service and your friends might also subscribe to the service. So you're both using the same service, but all of your information, so things like what music you like, your play history, your playlists, your recommendations are all just for you. But then to add some complexity, you might also have a family that can subscribe together. And maybe they can share a billing account. Maybe they can even share data like a family playlist. So in this example, tenants might represent users or even families. And we call this a business to consumer or B2C solution. Now, at this stage, it's important to clarify who the audience for our guidance is. So firstly, startups and other what we call independent software vendors, ISVs, might choose to build and make their own software available as a service. So either to businesses or to consumers, as we've just talked about, or both. This is based on their business model. And most SaaS, most software as a service systems, are multi-tenanted. That's part of their business model. And an ISV might deploy their solution to the customer's own environment as well. That's a form of multi-tenancy too. But there are also other multi-tenant systems that aren't created by startups or ISVs. So for example, if you work in an enterprise, you might have a platform team that builds centralized platforms and resources like API gateways, shared Kubernetes clusters, networking resources, things that other teams will share and build on. And I would say that these systems are also multi-tenanted as well. So although it can be a little tricky to pin down a definition for what a tenant is, there are a few things that can typically indicate who tenants might be. So generally a tenant is a customer, somebody that we have a commercial or a billing relationship with. The tenant might just have one user, like in our music streaming example, or there could be many users associated with the tenant, like in the accounting system example. A tenant might be an organization. It might be a team or a division within an organization. It might be a family. And tenants represent some sort of security boundary with their own data. And tenants also have the illusion that the system is dedicated to them. It's not, but of course that's the impression they get. So the definition of a tenant will be different for different scenarios and different solutions. But when we think about a multi-tenant solution, we're really thinking about a system that can serve multiple tenants, however you define those. And this implies multiple customers and multiple users. Now, a multi-tenant service could also could just be serving a small number of tenants. So for example, imagine you're building a very, very niche accounting system for a specific industry, or maybe a shared platform for an enterprise. Or it might scale to millions of tenants, like if we're building a music streaming service. Now, as we talked about earlier, multi-tenancy doesn't mean that every single aspect of our system is shared, but there's some level of sharing of resources. So this might just include the application binaries, but it could also include some of the data, or even all of the infrastructure. And the degree to which you share your resources and the ways in which you share them are decisions that you as the platform vendor need to make, because they give you efficiencies in your costs and management. But your tenants also have their own requirements. They're very likely going to expect some level of degree of isolation of their data. And they probably expect that the performance of the system is going to be consistent, regardless of who else is using it at the same time as them. So you need to think very carefully about isolation and try to find the right balance between meeting your tenants' requirements and getting the level of efficiency that you're looking for. Now, isolation isn't just a binary decision. There's a spectrum of isolation options available when you're architecting a multi-tenant solution. So let's imagine a hypothetical multi-tenant service that serves 3 tenants. So the service is very simple, architecturally speaking. It's just got a web server and a database. So you can imagine the same fundamental architecture could apply to many, many different examples. So all the way at the very left of our isolation spectrum, you might consider deploying completely separate resources every time a new tenant is onboarded. So essentially, every tenant has their own private environment. We often call each of these individual deployments a stamp because you're stamping out a new instance from some sort of template. Now, this option typically involves the highest resource cost because none of your Azure resources are shared. So if one tenant is idle for most of the day, you still have to pay for all their resources and you can't make them available to another tenant to use instead. But tenants get completely isolated environments. And for some kinds of workloads or for regulatory environments, that might be the only option available. And it also tends to be the simplest to implement as well. And generally, you use the same code and the same deployment scripts for each tenant. So you're getting benefits from having that layer shared between tenants at least. Now, you can also move slightly towards the right of the slider by sharing stamps between some of your tenants and then using dedicated instances for others. We call this vertically partitioning your deployments. I should note the term vertical partitioning that we use is something that we've used in our documentation, but we might look at changing it if we can think of a better name. One of the reasons you might do this is if you have a tenant who is very sensitive to performance. So for example, if they have very strict data isolation requirements. So in this example, tenant C has their own dedicated deployment. You can also use this approach to scale out your solution globally as well. You might deploy one instance of your solution in the United States, another in Europe, another in Australia, and then your tenants can use the deployment that's closest to them and it'll give them the best performance. You can also use this approach to implement different price tiers with different service levels. And you can use it to roll out new versions of your solution progressively instead of deploying to all of your tenants at once. Another option is to share some of the resources between all of your tenants. And then in certain parts of your solution, you also dedicate certain resources to specific tenants. Now, most commonly, this will be something like a database or a storage system, like in the example here. And each tenant gets their own database in this case, but they share the same web server. So if your database tends to be the busiest component of your system, then this means that you can avoid some of the concerns around how one tenant's use of the system might impact another tenant's use. It also makes it less likely that you'll run into some of the limits and quotas that we'll discuss shortly. And you can do this while maintaining some of the shared resources, which means that you get cost benefits for those at least. To adopt this model, you're going to need to clearly understand which of your components will be dedicated and which will be shared and why. So for example, you might make that decision based on performance, or it might be based on meeting certain compliance requirements for your tenants as well. And finally, we could consider sharing everything. Every tenant accesses the same web server. All of the data for all of the tenants is stored on a single database. It'll be marked with a tenant ID, of course, but it's in the same tables or containers. And we call this a fully multi-tenant system. Now, this can give us some enormous cost advantages because we can make very effective use of the resources that we provision. It also makes it very easy for us to manage the system because everything is in one place. And so we minimize the number of resources that we need to configure and monitor and so forth. And we can also take advantage of having multiple tenants too. So take our music streaming example earlier. A multi-tenant music streaming service might do things like training recommendation engines based on every tenant's listening data and then create shared machine learning models that everybody gets the benefit of. But we need to be very careful to separate out our tenants' data in this kind of architecture, especially if it's sensitive. Our application code needs to be really careful to include tenant IDs on every database request, for example, and not to accidentally leak data between tenants. And we also need to be conscious of ensuring that one tenant can't take up more than their fair share of resources, which we'll talk about shortly. And if we get to a large number of tenants or a lot of requests or a lot of data flowing through our system, then we need to consider whether we'll reach any of the limits or quotas for our resources. So as you can see, there are a lot of different ways in which you can isolate your resources. And in this example, we've just considered a really simple architecture with a web server and a database. But this decision can get a lot more complicated when you start to introduce other resource types. So you can think about whether you share or isolate resources like networking and monitoring and logging, data analytics, machine learning models, messaging, identity, and even IoT services. Each of these categories has their own separate set of considerations and concerns, which we talk about in our guidance, and I'll cover some of these in more detail soon. But for now, I want to switch to talking about another important concept in multi-tenancy, which is limits and scaling. So let's go back to our example from before about having some fully dedicated deployments for each tenant. When we deploy these in Azure, we probably deploy each one into its own resource group. And most of the time, those resource groups will be deployed in a single subscription. And as we grow and onboard more tenants, we just keep deploying more and more resource groups with the same types of resources. So we continue to grow and grow. Eventually, we get to over 900 deployments. And then when tenant number 980 comes along, suddenly we get a deployment error. The reason for this is that Azure has a number of limits that we need to be aware of. They're all documented in this example, which is at this URL here. And if we scroll down and look at the subscription limits, we can see there's a limit of 980 resource groups in a single subscription. So the way to work around this is to stop at 979 resource groups, or ideally well before then, and then scale our deployments across multiple subscriptions, each of which can contain up to those 980 resource groups. So you can see here that how your isolation model can really affect your ability to scale and how you need to plan your solution based on the level of growth that you expect to get. Now, this isn't only an issue when you're deploying dedicated resources. Azure resources also have other limits that apply to their configuration or to the way they're used. So for example, imagine that you're building a completely shared storage account for all of your tenants to use. So when you only have 3 tenants, that works great. It might even work well when you have 100 or even say 1,000 tenants. But at a certain point, you might try to exceed the 20,000 requests per second limit that a storage account has. And suddenly you get request failures. Now, in many cases, you can actually request that these kinds of limits be raised, but there will be an upper limit somewhere. So you need to consider deploying multiple storage accounts and spreading your requests across them if you're going to be getting to a high scale. But of course, you need to decide this based on your own requirements. If you know for certain that you will never get to a large number of tenants or a large number of requests per second, then this isn't something you're going to need to worry about. But in general, scaling out across multiple resources or resource groups or subscriptions is an important concept and something that you need to carefully consider. So now I'd like to talk about some of the architectural approaches that we discuss in our guidance. And I'm going to start by talking about resource deployment. We just talked about scaling out and deploying tenant-specific resources. And it becomes really critical to have a good plan for how you will onboard new tenants. This includes everything from establishing commercial relationships to understanding any particular requirements the tenant has, like data residency or isolation requirements, and even things like how you're going to handle custom domain names, TLS certificates if they're provided by customers, all those kinds of things. You'll need to decide whether you automate some or all of this process. And if you only have a small number of tenants and you're adding them fairly infrequently, then maybe you don't need to automate anything. But if you need to onboard tenants very quickly, or if you want to enable self-service onboarding, then you need to automate the entire process. And you'll need to plan how you deploy your Azure resources to serve your tenants. So let's consider a horizontally partitioned architecture with some shared application components and a single shared Azure SQL Server, and then with databases for every tenant. So similar to the approach we talked about before. Now, we somehow need to deploy those tenant-specific databases and potentially also need to make a note of the mapping between a tenant ID and a database, and maybe even store the connection strings for those databases or other information about the database. So one option is to store our tenant list in a configuration file somewhere. If we deploy our infrastructure as code using a tool like Bicep, then this could be just a parameter file that we use to drive our deployment. And then when the deployment runs, or the pipeline runs, it can provision the databases for each tenant defined in that file. So this approach works really well when you have a small number of tenants and when your team is directly involved in onboarding every new tenant. But it might take some time before a new tenant's database is deployed. So if this customer signs up, they need to wait for the next time this pipeline runs before they'll be able to use the system. Another option is to treat your tenant list as data and to have your application control how new tenants are provisioned. So you'll build something called a control plane, which might be triggered by a self-service tenant registration form or a CRM or Azure Marketplace or something else. And then when the control plane receives a request to add a new tenant, it triggers a workflow. And the first thing the workflow does is deploys the new tenant's database. Then the workflow can update a tenant list, a shared tenant list somewhere central, to include the new tenant's information, as well as things like their database details or their connection string. Now, this works really well when you need to support self-service onboarding, but you need to have a clear distinction between the two types of resources. First, you need to consider the resources that are dedicated to each tenant. So those are going to be provisioned and managed by your application code. And then second, you have the resources that aren't dedicated to a tenant, they're shared. And those are provisioned and managed by your deployment pipeline. Each of these two types of resources needs to be tracked and managed separately. And you don't want to mix them up. Now, you can choose to sell a SaaS solution, a software as a service solution, through the Azure Marketplace, and this reduces the friction for your customers to subscribe. So Azure Marketplace interacts with your solution's control plane to trigger the kinds of workflows we just discussed to manage the full lifecycle of your tenants. So to trigger the onboarding process and also offboarding and other things. So you need to build those onboarding and lifecycle management workflows yourself. But your tenants will get a consistent experience because Azure Marketplace plugs into those. And those onboarding processes that you use might trigger automated deployments. Maybe even they'll just trigger a manual process that requires someone in your team to perform the onboarding steps. And again, if your requirements are that you don't need tenants to be onboarded quickly, then that might be perfectly fine. Okay, so now we're going to talk about some of the specific architectural considerations when you're building a compute tier. So by compute, we're talking about web servers, application services, background services, functions, and so forth. Basically anything that runs your own custom code. So when you build a multi-tenant solution, there are several things to consider about how your compute services run. We're going to talk through a few here, but of course, take a look at our guidance for a lot more detail on some other topics that we don't have time to cover here. So suppose that you have a fully multi-tenant architecture like the one we saw before, with a shared compute tier, and that could be Azure App Service, it could be Kubernetes, it could be container apps, it could be virtual machines, any other compute service. So let's just zoom in on the compute service here. Now, typically, when you build a cloud solution, you'll deploy your compute tier with a load balancer, and that's in charge of routing traffic between some number of worker instances. In a multi-tenant solution, as you start to onboard more and more tenants, you probably will need to scale out to more and more compute workers because the overall volume of traffic that you're getting is increasing. And so when you build a multi-tenant compute tier, it's important to consider how you plan to do that and to use features like auto-scale and event-driven scaling and good monitoring to ensure that your tenants experience acceptable performance. But it's also important to consider state, because for many multi-tenant systems, storing state on the workers can become a bit more complex. So let's take an example request. Suppose tenant C, in this case here, sends a request to the web service, and the load balancer randomly selects worker 4 to process that request. Now, as part of serving that request, worker 4 can retrieve some of the data about tenancy from a database, say, and then save it into a local in-memory cache or onto disk or something else on that worker. When a different user from tenant C sends another request to the application, the request might go to a completely different worker. The load balancer doesn't know. So it reduces the benefit of caching the data. Now, this might or might not be a problem depending on the volume of requests, the type of data that you're caching, and so forth. But if it is a problem for your solution, then one option is to make your load balancer smart and to try and send all of the requests from the same tenant to the same worker. This requires some sort of mapping of tenants to workers to be maintained by the load balancer. It also has the potential to create things called hot workers, which means you lose the benefit of scaling out because one worker becomes overloaded if there's an especially busy tenant. Another option is to use an external cache like Redis and to share it amongst all of your workers. And this can be a really good option, but it's probably not going to be as fast as in-memory caches. Now, the problem I'm talking about here, it can happen with any solution, but multi-tenancy exacerbates this problem because techniques that we might normally use to counteract them, like sticky sessions, don't tend to work. So again, whether it's a problem for your particular solution really depends on your needs. And there's another consideration for shared compute components, which is the noisy neighbor problem. So let's imagine that in the architecture that we just discussed, there are some operations that tenants perform that are very compute intensive. So maybe they involve a lot of CPU work, or maybe they do a lot of disk I/O. And basically, imagine that two tenants are using the system at the same time. So over time, if tenant A happens to consume a large amount of the total, a disproportionate amount of the total system capacity, anything that tenant B is doing could fail because the system's resources become exhausted. So this shows up as failures for tenant B, and they probably won't be very happy. You can even get the noisy neighbor problem if each of your tenants' workloads are relatively light, but they happen to overlap in a way that can exacerbate the problem. So for example, here, you can see that the total amount of system capacity used by any individual tenant is quite low, but overall, the system capacity gets used up to a pretty high maximum value, which means that any other tenants that start to use the system will see failures. So the noisy neighbor problem is an inherent risk in multi-tenant systems, but there are several different ways that we can look at mitigating it. So for example, we can deploy sufficient headroom in our performance to make it unlikely that it will happen. We can also model our tenants' access patterns and ensure that we allocate sufficient resources in anticipation of these kinds of problems. So if we know, for example, that most of our tenants use the system during the business day and not at night, we can use autoscale or other solutions to plan for the capacity that we need for those different periods of time. Or we can deploy multiple pools of resources and then ensure that each of the tenants share that pool have distinct workload patterns. So they're not going to kind of overlap and cause these issues. And then we can also make changes to our application as well. So we can perform throttling to enforce limits on each tenant, and we can use things like Azure API management, for example, or even application code to apply throttling and quotas and rate limits and those kinds of things. So now that we've talked about compute in a high-level conceptual kind of way, Paolo is going to talk a little bit about how we can apply some of these concepts in Azure Kubernetes Service. Paolo.
By now, everyone should know what it is. Can you go to the next slide, please? So everyone knows what is Kubernetes today. I mean, Kubernetes is, is a very successful system for hosting applications. It is extensively used by customers. So what is Kubernetes? Kubernetes is an open source orchestrator for automating deployment, scaling, and management and monitoring of containerized applications. So initially was developed by Google as a project, then it was donated to the Cloud Native Computing Foundation. If we go to the next slide, we can see that Kubernetes provides a very rich set of features. This is mainly the reason why it's so successful. So for example, regarding pod scheduling, it can be used to schedule and place pods based on constraints. So for example, you can use tains, toleration, labels, node selectors, or pod affinity and anti-affinity rules, or even pod topology spread constraints to fine-tune the allocation of pods and the scheduling on particular nodes and node pools. Is also very well integrated with multiple DevOps systems. So Kubernetes provides out-of-the-box features for automated changes, rollouts, and rollbacks. Also, the ecosystem for deploying application is quite rich. Think about it. The Helm that provides a way to package and deploy workloads to your Kubernetes cluster, or customize that can be used, for example, for application configuration on different environments. So if you want to specialize and customize the deployment of workloads for different environments or even different cloud platforms, for example. It's very well integrated with all of the major DevOps systems, so GitHub Actions, Circle CI, Jenkins, GitLab, Azure DevOps, and so forth. And one of the methodologies that is emerging quite a lot and becoming more and more popular is GitOps, which is a way for implementing continuous deployment for cloud native applications, because it provides a way to, when you are deploying a GitOps solution like Argo CD or Flux, this is going to deploy a controller on your Kubernetes cluster that is continuously monitoring your Git repo, that is the source of truth, to see if a new version has been deployed, and is using a pull model to eventually deploy a new version of the application on your Kubernetes cluster. On the storage side, Kubernetes support so-called container storage interface that provides the ability to integrate and expose many different file systems to containerized workloads. For example, on the Azure platform, you can use Azure Managed Disk and Azure Files, but you can integrate many third-party distributed storage file systems. So you can, as I said, you can leverage a very rich ecosystem. For example, you can use Rook, GlusterFS, Portvox, and so forth. From a network standpoint, Kubernetes provides a very, very rich set of capabilities. For example, when deploying an Azure Kubernetes cluster, you can choose between KubeNet or Container Network Interface. When, for example, using the Container Network Interface, your pods have, they get a private IP from the subnet. Network policies are very useful, as we'll see in the next slide, for multitenancy to isolate different tenants running in different namespace. And then Cloud Platform also provides features to protect the access to the control plane, which is very important. For example, AKS provides two different ways to protect the API server, which represent the REST API exposed by a Kubernetes cluster. You can use a private cluster, or you can use authorized IPs to constrain the access to these control plane to a specific range of public IPs. From a governance perspective, you can enforce policies using third-party solutions like Open Policy Agent and Kyverno. And also talking about container images that are used by your containers running on Kubernetes cluster. Typically, container registries and third-party solutions provide features for vulnerability scanning, so that before deploying a new version of your application, you can make sure that your containers do not contain vulnerabilities. Then there are many other features, because Kubernetes can also support batch execution, so through jobs. It provides also the ability to support both EBv4 and EBv6, so dual stack. Self-healing, when a container fails, is restarted on another node, and so forth. Now, let's look at in the next slide what are the features provided by Kubernetes for multi-tenancy. So you have two kinds of isolation that you can achieve. The first one, and the most simple one to achieve, is the so-called physical isolation. Basically, you can create a dedicated cluster for every tenant or every team. So while this solution is easier to achieve, is not the best one, probably from a management perspective, but also from a financial perspective, because you end up having a lot of cluster to maintain, and also because it doesn't provide a very good pod density. An alternative solution is using a so-called multi-tenant Kubernetes cluster. In this case, the cluster is shared across multiple tenants, by multiple workloads, and by multiple teams. So the way to isolate tenants is the namespace. So the namespace represent the isolation boundary in this context. So you can, for example, in a SaaS provider scenario where the same cluster is shared across multiple tenants, and you have a separate instance of the same application running on the cluster, one for each tenant, you can deploy every instance in a separate namespace. Now, you can use Kubernetes role-based access control and network policies to enforce tenant isolation at the security and network level when using namespace. So, for example, with network policies, you can avoid that the front end application is invoking the backend application of another instance of the same app running in a different namespace. To avoid the noisy neighbor problem that John just explained, you can also use a limit and request on the container level. But in order to enforce default limits, you can also use the limit ranges, or you can use resource quotas so that you can enforce limits in terms of CPU and memory at the namespace level. This way, you are guaranteed that no tenant can, consume all of the system resource in terms of CPU and memory from the shared cluster. In addition, you can enforce safeguard and security standards by using policy engines. The Azure platform is providing support for the open policy agent through the Azure policies, but you can also leverage a third-party solution like Kyverno. The logical isolation that you can achieve by, using a shared cluster provides a better pod density and also provides the ability to scale out and scale in the number of pods based on the traffic conditions on a demand basis. So you can use CPU and memory metrics to scale out and scale in the number of pods on a per tenant basis. Or you can also use Kubernetes event-driven application, also known as KIDA or KEDA, that provides the ability to auto-scale your cluster based on the metrics of external services that could be Kafka, could be Azure Service Bus, could be Azure Event Hubs, and so forth. So Kubernetes also provides the ability to auto-scale the number of nodes based on the current demand. So this is very helpful to keep under control the total cost of ownership, because you can dynamically scale out and scale in the number of nodes based on the traffic conditions. Finally, if you want to have a better resiliency, you can also use the pod topology spread constraint to spread your pods across the availability zones within a region. So it's important that you deploy clusters. So for example, in Azure Kubernetes Service, you can deploy cluster across availability zones, but also when deploying your workloads, you are using the pod topology spread constraint to make sure that you have at least one replica in each availability zone. And finally, I like to remark the fact that you can also leverage third-party frameworks like Capsule. Capsule, for example, provides the ability to basically to create a so-called custom resource definition that is called, guess what, tenant. So you can associate multiple namespaces to a single tenant. And it's a way to logically divide a shared cluster across multiple tenants. KubeCost is another interesting solution that you can use to break up the cost across different namespaces. And so this way you can charge back costs of a shared cluster to each tenant based on their actual consumption.
All right, thanks, Paulo. So next, I'm going to talk about multi-tenancy in the storage and data tier of a multi-tenant application. And we can really categorize these design decisions into 4 categories here: scale, isolation, complexity, and cost. So when we look at scale, one of the first things we want to understand is the number of tenants that we're likely to be dealing with. If your solution is going to be hosting thousands of tenants, your architecture is likely going to be a lot different than if you're only hosting 5 or 10 tenants. We also need to look at the amount of storage that each tenant is likely to consume. We also need to look at the total storage of the workload. And then we need to look at the actual workload that we're applying to the database itself, because if customers are using the database for 24 hours, around the clock at 100%, that's going to work in your favor for certain architectures, but not for others. The next thing we need to look at is isolation. And there are 2 types of isolation. The first is data isolation, which is just separating one tenant's data from another tenant's data. The design choices around this are frequently driven by contractual or regulatory compliance. This usually can be looked at as sort of the first thing you need to consider, because you need to know what your requirements are around this so you can design the right data structures and the right infrastructure underneath the data tier. The next is performance isolation, and John talked about this earlier. This is effectively the noisy neighbor problem. You want to be able to sort of segregate customers from a performance standpoint. Now, if it's a B2C application like a mobile app, you may not have as many concerns about one customer impacting the others, because the amount of data they're storing in your database is probably pretty small, and you're probably doing single lookups. So that's a little bit of a different, that's a big concern for these types of systems, and a little bit of a different look at how you would design those. The most overlooked category is complexity. This is things like, how am I going to implement a schema change in a database? Do my developers have the necessary skills to develop for the data platform that I would like to use in my solution? How am I going to monitor this solution? And am I going to have to charge back customers for the amount of storage they're using and things like that? So those are important. Also, is the solution going to meet my high availability and disaster recovery needs? And is that going to be a complex solution, or is that merely just turning on a switch and having a feature available to me to make that happen? And then finally, on complexity, we have customization. If you offer per tenant customizations, that adds significantly to your complexity. Finally, we have the cost. And this is not just the overall cost, but the cost per tenant. And you'll sometimes hear this referred to as the tenant density of the solution. So you need to consider all of these factors when designing the solution. So what we're going to look at next is a few of the more common patterns that we see in the Fast Track for ISVs group. The first is the single database per tenant model. This is a highly scalable model, but it is limited to what can be provided by a single database. It does provide the strongest isolation, as John pointed out before. It also gives you very simple per tenant data management. And this is another factor that tends to get overlooked. So for example, if tenant A accidentally deletes all their data and I have a multi-tenant database, how am I going to restore that, right? So that if I'm using a single tenant per database, it's easy. I can just restore their entire database and it has no impact to the other customers. Now, while this does provide strong isolation, it also tends to be the most expensive. But if you want to try to control the cost, look for features and services that can allow you to pool resources together so that all your tenants can share a pool of resources, as opposed to provisioning resources at the tenant per tenant level. And then finally, you can use catalog databases if you have a large number of tenants. That helps ease the lookup of tenant metadata. Next, we have the single multi-tenant database. And this is what most people think of when they think of a multi-tenant system. This does give you the highest tenant density and the lowest per tenant cost. It also gives you the lowest isolation, and it's very susceptible to noisy neighbor issues. And this makes this particular architecture not well suited for a lot of types of applications, because if the tenants are too busy for too much of the day, they're inevitably going to have an impact on the other tenants in the system. In this model, per tenant customizations can be incredibly challenging. Past a few customizations, it becomes almost unmanageable. And then management of the tenant data is always a challenge here. Restoring a single tenant's data in a database that has hundreds of tenants in it, you don't want to take the whole database down just because tenant A accidentally deleted their data. So there are some, while from a cost perspective, this is a great solution, from a management and overhead standpoint, it can be unwieldy to manage if you don't have good solutions for those problems. Next is the sharded multi-tenant database. And this is sort of a hybrid of the previous two solutions that we looked at. This is when your tenants are distributed across databases that are usually called shards. Each shard may have one tenant, or it may have multiple tenants. And the idea is that you can spread your tenants out across a set of databases and reap the benefits of effectively infinite scale out. Now, tenants don't have to belong to a single shard. They might cross shards. And in that case, you almost for sure have to have a catalog database to help you manage that. And it adds to the complexity. This is still highly susceptible to noisy neighbor issues. And it does give you very high tenant density, though, just with a lot of additional complexity because you have to manage all the shards. All right, and I'm going to close out with some patterns and anti-patterns that we typically see customers challenged with in the ISV space. Do consider row-level security if your database model requires it. So anytime when you have multiple customers in the same database and you allow any type of ad hoc access, you're almost for sure going to be looking for some type of row-level security to help keep that in check and guarantee that tenants can't see each other's data. Tenant-level encryption is another one. Not just tenant-level encryption, but a lot of tenants, especially in finance, healthcare, those types of industries where they have lots of PII data and financial data, want to manage their own encryption keys. And so that is something you might want to look into and make sure you're meeting those requirements. Pool resources where appropriate. That can save you quite a bit of money. Sharding tenants as well. And it's not just the horizontal sharding, but vertical sharding as well. So if you have, for example, a database with a lot of shared information in it, you can shard that off on its own. And then that way you're not replicating that data in every tenant database, things like that. Consider cost allocation. So if you are certain systems will allow you to allocate resources to individual tenants on a database by database level, which is great, and it's very easy for you to map that back to a tenant of yours. But if you are sort of putting all your tenants in single database, the same database, or in the same storage account, you need to know, what are your capabilities for monitoring for that so that you can allocate that cost to the correct tenant and know how much to charge your tenants in general. Some anti-patterns that customers struggle with. Table-based isolation is, while it works, if you put multiple tenants in the same database, you do schema schema isolation or something like that. We find that it gets unmanageable after with just a few 10, 15 customers in there. It starts becoming quite unmanageable. Custom schemas for different tenants is also an anti-pattern. This has big management overhead because if you change the schema of the table, suddenly your DevOps environment has to have provisions for updating to the same table with 2 different schemas underneath it and different columns and things like that. So that becomes unmanageable as well. Manual schema changes. You want to make sure you have a way to deploy schema changes. Manual schema changes can be very error prone, for one, and also you frequently you won't have a good grasp on which schema changes have completed on which databases, and you won't know which ones at which version, and that can be difficult to manage. And so coming up with proper DevOps practices will help you manage that. And then finally, version dependencies. You want to try to write your application such that it's not any, there's as little dependency on a specific version of the database as possible. And if you do have dependencies on that, for example, relational databases, then you want to try to maintain compatibility at least one if not 2 versions back, so that when you're rolling out, you can roll out, you won't have to roll out simultaneously to all of your tenants. And with that, I'm going to pass it back to John, and he's going to talk about cost management.
Thank you, Paul. So I'm going to talk now about another important aspect of managing a multi-tenant solution on Azure, which is tracking and allocating and managing your costs. And Paul alluded to this a minute ago as well. Azure provides some great features to track and allocate costs. So these include things like resource tags. So in this example, every resource can be tagged with a deployment stamp ID, and resources that are dedicated to specific tenants can be tagged with that tenant ID. Resource tagging like this works really well when you have resources that are dedicated to specific tenants, because Azure very clearly breaks down the cost for every tenant. But it's a bit more challenging when you have shared components, whether they be databases or compute services or anything else. So another way to track and allocate costs for a multi-tenant solution is to instrument your software. So for example, you can measure the number of API requests that each tenant makes, and then use an access token to identify the tenant for each request. And then you can build a billing metering system on top of that. And you can do that in a lot of different ways. So one approach that can work well for a very high volume application is to use a system like event hubs to track every incoming request as an event, and then to use Stream Analytics or another service like it to aggregate all those events and write out the total number of requests per tenant to a database. But it's important that you use a system that's actually designed for this kind of data. So for example, a lot of customers use application insights, but that isn't a good choice for handling things like billing data or usage data, because it's designed to do things like data sampling, which means the individual records aren't always accurate or complete. For the purpose that it's intended for, that's not an issue, but for billing and kind of cost management purposes, that is a really big problem. So that leads to another consideration that you need to think about as well, which is the level of precision that you need to track costs at. And this really comes down to the purpose of measuring costs. So if your purpose is to bill tenants directly for their Azure resource consumption, then the accuracy of those costs is probably very important. But if you're running a shared multi-tenant system, then probably all you need is to have an approximate idea of your costs. And maybe you're interested in things like whether specific tenants are using the system a lot more or a lot less than others. And of course, you need to think very carefully about how you allocate those costs for shared components, because even things like request counts and instrumenting your APIs might not give you a true picture of how much a specific tenant costs to run. Not all requests are actually equivalent in terms of the amount of cost they incur. But it's a good idea not to over-engineer this either. Most of the time, for most solutions, an approximate cost breakdown is sufficient, and going more than that is over-engineering it. So that leads to the final area that we're going to talk about today, which is the types of pricing models that you can consider if you're providing a multi-tenant solution as a service, for example, as a SaaS product. Pricing models are complex, and the pricing model that you select will matter a lot for your architecture and for your organization. As usual, I'll provide a brief overview of some of these topics, but take a look at our guidance for a lot more detail. So we've already mentioned one pricing model, which is to simply bill your tenants for the cost of the resources that are used to serve their requests. Now, this can be a good option in an enterprise scenario where you're not operating a multi-tenant system to make a profit. You just need to recover your costs from other teams. So you find out what those costs are and then bill them on. But in a SaaS solution, if it's your business, then it's common to look at other pricing models. And of course, your company's business model will have a lot to do with this. Now, a simple pricing model is just to charge every tenant a flat rate. So regardless of how much they use the system, they pay the same price, say, every month. But if your instrumentation shows that some of your tenants use the system dramatically more than others, then this might be an unfair distribution of your costs. So instead, you could look at billing for the amount of use by each tenant. And so as a tenant uses the system, their bill goes up. But of course, this can make it difficult to predict your revenue and your costs. And it also means that tenants might be motivated to actually use your system less, which is probably not what you want. Another model that many SaaS solutions have is a freemium model. So this is where you get some sort of set of capacities or capabilities for free, and then the tenant needs to pay more to unlock more capabilities. So for example, your free tier might not provide a service level agreement or any kind of guarantees. There might be limits on how many API calls they can make each month, and you might only allow, say, 10 users within a tenant. But then if the tenant moves to a paid plan, they'll get support, they'll get an SLA, they'll be able to use the API as much as they like, and maybe they can have a lot more users as well. Similarly, you might not provide a free tier, but you might instead provide multiple tiers at different price points with different feature sets. Now, when you use the freemium or this tiered pricing model, you need to think carefully about how you'll enforce these kinds of rules architecturally. So for example, how will you enforce API limits on your lower tier customers? Services like Azure API Management can let you do that. And how will you enable features depending on the tier that the customer is at? Can you use things like deployment stamps? And if so, how? And if you need to give your gold tier customers some sort of performance or isolation guarantees, then maybe you need to deploy dedicated infrastructure for those tenants by using some of the isolation models we spoke about earlier. So whichever pricing model you choose, remember that you need to be able to actually implement it. If your pricing model relies on knowing how many requests the tenant is sending, then make sure you understand exactly how you're going to meter those tenants' usage and tally them up, and how you're going to audit that if necessary. And if your pricing model is based on things like applying limits to some tenants, then ensure that you'll know exactly how you'll enforce those limits. And if you use a tiered pricing model, consider how you'll enable and disable features for each tenant. So this is a really good illustration of how your architecture is very tightly linked to your commercial decisions and to your requirements. So that brings us to a few points to take away when you're architecting a multi-tenant solution on Azure. So first, it's important to have a very clear understanding of your tenants' requirements and not to make unfounded assumptions. So for example, do your tenants have an expectation of an uptime SLA? Do they have data isolation or data residency requirements? Do they need you to meet specific compliance standards? Unfortunately, customers have a funny habit of not telling you some of these things until it's too late. So it's important to be clear upfront. Second, you need to consider your own business model and requirements. It really matters a lot whether your company treats the system as a cost center or a profit center. Think about your own growth plans. It's important not to over-engineer for unrealistic levels of scale and growth, but you also don't want to under-engineer and get caught short or lose customers because of things like noisy neighbor issues due to unplanned scale. Third, there are lots of different types of multi-tenancy patterns and models that you can follow. And the way to select the right ones for your solution is to have your requirements front of mind. Multi-tenancy doesn't necessarily mean, of course, that everything needs to be shared across every tenant. So remember, you've got lots of options. And finally, we're here to help. We've put together this guidance that covers everything we've talked about today, as well as a lot more. So please take a look and provide your feedback on anything that you think that we should add or change. So with that, please take a look at our guidance. The links are there. We're also very interested in your feedback, both in terms of the content that's already published, as well as any suggestions or requests for future content that relates to multi-tenancy as well. So you can see those links there to provide us with that feedback. So I think we're pretty much at time. So I don't think we'll have any time for questions right now, but feel free to drop them in the chat. Our moderators can answer any questions there. And thank you very much for your time today.